We have stood on the edge of a neutron star, where gravity crushes atoms into a sea of neutrons, where a teaspoon of matter weighs more than a mountain. We have witnessed pulsars spinning hundreds of times per second, their beams slicing through space like cosmic lighthouses. We thought we had reached the limit of density, the final word in stellar collapse. But nature is not done surprising us. For beneath the surface of some of these stellar corpses, a deeper transformation may be taking place, one so profound it challenges our understanding of matter itself. What if neutrons are not the end? What if, under even greater pressure, they dissolve, shattering into their most fundamental components? What if, hidden in the silent hearts of dead stars, there exists a form of matter so dense, so alien, that it rewrites the rules of reality? This is the story of quark stars, not neutron stars, not black holes, but something in between, a theoretical object so extreme it exists only at the edge of known physics. A star not made of atoms, not even of neutrons, but of the raw building blocks of existence, quarks, free, unconfined, flowing in a quantum ocean deeper than space, older than time. We have never seen one, not for certain. But we are beginning to feel their presence in the cooling curves of ancient pulsars, in the silent collapse of massive cores, in the gravitational echoes of colliding stars. They may be out there, hidden in plain sight, masquerading as neutron stars, while harboring a secret at their center, a phase of matter so dense it should not exist, yet might be the most stable form of matter in the universe. To find them, we must journey beyond the limits of Earth-based physics, beyond the reach of particle colliders, into the hearts of stars that died long before our planet formed. This is not just a search for a new type of star. It is a quest to answer one of the oldest questions in science. What is matter when crushed beyond breaking? When a massive star dies, it does not go quietly. In a supernova explosion, brighter than a billion suns, its outer layers are blasted into space, seeding galaxies with carbon, oxygen, iron, the elements of life. But at the center, something far stranger is born. A core so dense, so compact, that light bends around it, time slows to a crawl, and the very concept of solid loses meaning. If the core is less than about 2.3 times the mass of the Sun, it becomes a neutron star, a city-sized remnant spinning in the dark, its surface gravity so intense that if you dropped a marshmallow onto it, the impact would release more energy than 1,000 nuclear bombs. But what happens inside? At the surface, the star may still resemble familiar matter, a lattice of atomic nuclei and electrons frozen into a crust harder than diamond. But just meters below, pressure rises to levels no laboratory can replicate. The atoms are crushed. Electrons are forced into protons, turning them into neutrons. The entire star becomes a single, gigantic nucleus, a neutron fluid governed by quantum mechanics and general relativity. This is the realm of the neutron star, but it may not be the final state, because as we dive deeper toward the core, the density climbs beyond 100 million tons per cubic centimeter. Neutrons begin to touch, then overlap, then dissolve. At this point, the strong nuclear force, the glue that holds quarks inside neutrons, may no longer be able to contain them. The boundaries between particles vanish. Neutrons cease to exist as individual entities. Instead, their constituent quarks, up, down, and possibly strange, break free, forming a continuous, ultra-dense fluid known as quark matter. This is not a gas, not a liquid, not a plasma. It is something else entirely. a deconfined quantum fluid where quarks move freely but interact through the strongest force in nature. In this state, matter may enter a phase of color superconductivity, where quarks pair up in ways that defy classical intuition, conducting color charge without resistance. A phenomenon predicted by quantum chromodynamics, but never observed at macroscopic scales. If such matter is stable, and if it can exist outside the extreme pressure of a stellar core, then the universe may have a new ground state, not iron, not neutrons, but strange quark matter. And if that is true, then every neutron star could be a ticking time bomb, a metastable object waiting to collapse into something far stranger. The idea that matter could exist in such an exotic state was first proposed not in the glow of a telescope, but in the quiet of theoretical physics. In 1971, physicist Arnold Bodmer published a paper that would quietly echo through the decades. He suggested that under extreme pressure, nuclear matter might collapse into a new, more stable form, one where quarks were no longer confined. He called it collapsed nuclei, a state so dense that protons and neutrons dissolve into a homogeneous soup. At the time, the idea was ignored. The standard model was still being built. Quarks themselves had only been theorized a few years earlier. The notion that they could exist freely, especially in bulk, seemed far-fetched. But in 1984, the idea was revived and radicalized by Edward Witten, one of the most influential theoretical physicists of the modern era. In a brief but revolutionary paper, Witten proposed that not only could quark matter exist, it might be absolutely stable. He called it strange matter, a form of quark matter rich in strange quarks, which could be more stable than even the most tightly bound atomic nuclei. If true, this would mean that neutron stars are not the endpoint of stellar collapse, but a temporary phase. Given enough time or sufficient pressure, they could undergo a phase transition, converting entirely into quark stars, or strange stars as they're sometimes called. Witten's idea was not just speculative, it was dangerous. Because if strange matter is stable at zero pressure, meaning it doesn't need the weight of a star to hold it together, then a single fragment, a strangelet, could, in theory, convert any normal matter it touches into more strange matter. A chain reaction, a cosmic ice 9. This sparked both excitement and alarm. In the late 1990s, before the relativistic heavy ion collider, RHIC was turned on, scientists seriously debated whether creating quark-gluon plasma in a lab could trigger a catastrophic conversion of Earth into strange matter. The consensus? The risk was negligible. Cosmic rays had been colliding with neutron stars for billions of years without turning the galaxy into strange matter. But the fact that the question was even asked shows how profound the implications are. Still, the idea persists. If strange matter is the true ground state of matter, then the universe may be littered with quark stars, silent, ancient, and more stable than anything we've ever known. To understand how such a star could form, we must return to the moment of a supernova, when a massive star collapses its core. About 1.5 times the mass of the Sun, implodes in less than a second. The outer layers rebound, creating a shockwave that tears the star apart. But at the center, gravity wins. The core is compressed beyond the density of an atomic nucleus. At first, the collapse is halted by neutron degeneracy pressure, a quantum mechanical force that prevents neutrons from occupying the same state. This is what creates a neutron star. But neutron degeneracy pressure has its limits. According to general relativity, there is a maximum mass a neutron star can support, the Tolman-Oppenheimer Volkoff limit. For decades, this was thought to be around 2.2 solar masses. But recent observations have found pulsars like PSR J074W Plu 6628 at 2W8 solar masses and PSR J0952 0607, possibly as high as 2W-tron stars, are pushing the limits of known physics. If they were made purely of neutrons, their cores should have collapsed into black holes long ago. Yet they remain stable. One explanation? The core has already undergone a phase transition. The neutrons have dissolved. The star is no longer a neutron star, but a quark star, or at least a hybrid star with a quark core. This isn't just a theoretical escape hatch. It's a prediction of quantum chromodynamics, QCD, the theory that governs the strong force. Under normal conditions, quarks are confined within protons and neutrons by color confinement. You never find a free quark in nature. But at densities several times greater than nuclear density, the energy cost of confinement may exceed the benefits. The system lowers its energy by deconfining. Think of it like ice melting into water. At low temperatures, water molecules form a rigid lattice, but add heat and the bonds break. The solid becomes a liquid. Similarly, at extreme densities, the lattice of neutrons may melt into a fluid of quarks. But neutron degeneracy pressure has its limits. According to general relativity, there is a maximum mass a neutron star can support, the Tolman-Oppenheimer-Volkoff limit. For decades, this was thought to be around 2.2 solar masses. But recent observations have found pulsars like PSR J0740 Pu 662 at 208 solar masses and PSR J0952 0607 possibly as high as 2.35 solar masses. These massive neutron stars are pushing the limits of known physics. If they were made purely of neutrons, their cores should have collapsed into black holes long ago, yet they remain stable. One explanation? The core has already undergone a phase transition. The neutrons have dissolved. The star is no longer a neutron star, but a quark star, or at least a hybrid star with a quark core. This isn't just a theoretical escape hatch. It's a prediction of quantum chromodynamics, QCD, the theory that governs the strong force. Under normal conditions, quarks are confined within protons and neutrons by color confinement. You never find the free quark in nature, but at densities several times greater than nuclear density, the energy cost of confinement may exceed the benefits. The system lowers its energy by deconfining. Think of it like ice melting into water. At low temperatures, water molecules form a rigid lattice. But add heat, and the bonds break. The solid becomes a liquid. Similarly, at extreme densities, the lattice of neutrons may melt into a fluid of quarks. This phase transition could happen gradually, a quark core forming in the center surrounded by neutron matter, or suddenly in a burning front that converts the entire star in milliseconds. In either case, the result is a star that looks like a neutron star, but behaves like something else. The differences may be subtle, but they are measurable. Take mass and radius. Because quark matter is more compressible than neutron matter, a quark star of the same mass would be slightly smaller. A neutron star might be 12 to 14 kilometers in radius. A quark star could be as small as 9 or 10 kilometers, still city-sized, but noticeably more compact. This is where telescopes like NISA, Neutron Star Interior Composition Explorer, come in. Mounted on the International Space Station, NISA measures the X-rays emitted from hotspots on pulsars as they spin. By analyzing how the light bends around the star's gravity, scientists can infer both mass and radius with unprecedented precision. And some of the stars it has observed are Strange. PSR J03 low, J03 plus 0451 for example, has a mass of about 1.3 solar masses, but a radius of only 11.2, 12 kilometers, smaller than many models predict. PSR J0740 plus 6620, despite its high mass, appears to have a radius no larger than 13 kilometers. These values are difficult to explain with pure neutron matter, but they fit beautifully with models that include a quark core. Then there's cooling. Neutron stars are born hot, over 1 billion degrees Kelvin. But they cool rapidly as neutrinos stream out from their interiors. The rate of cooling depends on the particles involved. In a standard neutron star, neutrinos are produced through processes like the direct Urca process, where neutrons decay into protons, electrons, and neutrinos. But in a quark star, new pathways open up. Quarks can annihilate or change flavor, producing neutrinos far more efficiently. This means a quark star should cool much faster than a neutron star in its first few hundred years. And there are candidates. The neutron star in Cassiopeia A, the remnant of a supernova observed in 6080, is only about 330 years old. Observations from the Chandra X-ray Observatory show that its surface temperature has dropped by about 4% in just over a decade, an astonishingly rapid decline. Standard models cannot explain this. But if the core underwent a phase transition to quark matter around the year 2000, releasing energy and accelerating neutrino emission, the cooling curve fits perfectly. It's not proof, but it's a signal. Another clue might come from glitches, sudden speed-ups in a pulsar's rotation. Neutron stars spin with incredible precision, but sometimes, without warning, they spin faster by a tiny fraction. These glitches are thought to result from the star's solid crust cracking or from vortices in the superfluid interior suddenly unpinning and transferring angular momentum. But in a quark star, the interior is not a superfluid of neutrons, it's a fluid of quarks, possibly in a color superconducting state. The dynamics would be completely different. A glitch in a quark star might look sharper, more energetic, or follow a different pattern. Some observed glitches are harder to explain with standard models. The Vela pulsar, for instance, experiences large glitches every few years. But the energy release and timing don't match predictions. Could a quark core be responsible? It's possible. Even more dramatic would be a starquake so powerful it triggers a phase transition. A sudden collapse in the core could release enough energy to be seen as a fast radio burst, FRB, or a gamma-ray flare. Some astrophysicists have proposed that certain types of mysterious cosmic explosions could be the birth cries of quark stars. Gravitational waves may hold the most definitive answers. When two neutron stars spiral together and merge, they send ripples through space-time that can be detected by observatories like LIGO and Virgo. The waveform of those ripples depends on how deformable the stars are, their tidal deformability. A stiffer star resists distortion more, while a softer one squishes more easily. Quark stars, being more compressible, would be more easily deformed. In the 2017 merger event, GW17 Height 17, the data suggested that the stars were relatively soft, consistent with either very dense neutron matter or something even softer like quark matter. Future mergers, especially those involving very massive neutron stars, could provide even clearer evidence. If one of the stars suddenly collapses during the merger, emitting a burst of neutrinos or gamma rays at the moment of contact, it could signal the formation of a quark star. And if the remnant survives for even a few milliseconds before collapsing into a black hole, its oscillation modes, its ringing, could reveal whether it was made of neutrons or quarks. There is also the possibility of bare quark stars, objects with no crust at all. Most models assume that quark stars still have a thin crust of normal matter, held up by electron degeneracy pressure. But if strange matter is absolutely stable, it might prevent the formation of a crust entirely. The surface would be a sharp boundary between vacuum and quark matter, a bare strange star. Such an object would have unique properties. Its gravitational redshift would be extreme. Its X-ray spectrum would lack the absorption features seen in neutron stars. And if it accretes matter from a companion, the material might be converted on contact, releasing energy in a flash. One candidate is RxJ 1856.5.3754, a nearby isolated neutron star. Early observations suggested it was only about 4 kilometers in radius, far too small for any known neutron star model. The finding was controversial, and later analyses suggested the radius was larger, but the initial result sent shockwaves through the community. A 4-kilometer object with a solar mass would have to be something far denser than a neutron star. A quark star? A bare, strange star? The measurements were ultimately deemed unreliable due to uncertainties in the atmosphere model, but the episode showed how close we might be to a breakthrough. We are not just searching for a new type of star. We are testing the limits of quantum chromodynamics, a theory that works brilliantly at low energies but becomes nearly impossible to solve at the densities found in neutron stars. On Earth, we can create quark-gluon plasma in particle colliders like the LHC. But those conditions are hot and fleeting. Trillions of degrees, lasting for a fraction of a second. The conditions inside a neutron star are cold and sustained, near absolute zero, compressed for millions of years. This is a regime of QCD we cannot simulate with full accuracy, not yet. So we rely on approximations, models, and indirect clues. We use equations of state, mathematical descriptions of how matter behaves under pressure, to predict what neutron stars should look like. Some allow for quark cores, others do not. The ones that do tend to predict slightly smaller, more massive stars, exactly the kind we're starting to see. Projects like the Square Kilometre Array, SKA, set to come online in the 2030s, will monitor thousands of pulsars with incredible precision, searching for tiny changes in spin or timing that could signal an internal phase transition. Future X-ray telescopes like Athena and gravitational wave detectors like Einstein Telescope and Cosmic Explorer will peer deeper than ever before. We may not have proof yet, but the case is building, and so we wait. In the silence between the stars, in the data streaming from orbiting telescopes, in the supercomputers simulating the strong force, we search for a whisper, a radius too small, a temperature too low, a glitch too sharp, a signal from the edge of existence. Because if quark stars are real, then the universe is stranger than we imagined. Not just denser, not just more violent, but fundamentally different. A cosmos where matter can melt into its most basic ingredients, where stars are not made of atoms, but of the stuff that came before atoms. A cosmos where the final state of matter may not be collapse, but transformation. We do not know yet whether quark stars exist. But we know where to look, and we know that if they are out there, they are waiting. Not in the bright centers of galaxies, but in the cold, dark outskirts, in the remnants of ancient explosions, in the quiet spin of a dying star. The next neutron star we observe could be the first quark star we've ever seen. We just don't know it yet. We have traced the path of a dying star, from supernova fire to the birth of a neutron star. We have seen how gravity crushes matter beyond recognition, turning atoms into neutrons, and neutrons into a quantum fluid under pressures no laboratory can replicate. But at the very heart of this collapse, something even more radical may be unfolding. A transformation so profound, it redefines the nature of matter itself. To understand what happens inside a quark star, we must first understand what a quark is, not just as a particle, but as a behavior, a state of energy, governed by forces so powerful they shape the very stability of matter. Quarks come in 6 flavors: up, down, charm, strange, top and bottom. But in the cores of stars, only 3 matter: up, down and strange. The others are too massive, too unstable to survive in bulk. Each neutron in a neutron star consists of 1 up quark and 2 down quarks, bound together by the exchange of gluons, massless particles that carry the strong nuclear force. This force is unlike any other in nature. It does not weaken with distance. In fact, it strengthens. Try to pull 2 quarks apart, and the energy in the gluon field increases until it creates a new quark-antiquark pair. This is color confinement. Quarks are forever imprisoned within hadrons. But confinement is not absolute. At extreme densities, 10, 20, even 50 times greater than that of an atomic nucleus, the average distance between quarks becomes smaller than the typical confinement scale. The individual hadrons begin to overlap, their boundaries blur, and at a critical threshold, the entire system undergoes a phase transition. Neutrons dissolve and quarks become deconfined. This is not a violent explosion. It is a silent transformation, a shift in the state of matter as profound as water freezing into ice, but occurring under conditions so alien they challenge our very definition of matter. The result is quark matter, a continuous ultra-dense fluid where up, down, and strange. Quarks move freely, interacting through the strong force. It is not a plasma in the traditional sense. It is not hot. In fact, it is cold, near absolute zero, cooled by neutrino emission over millions of years. But it is dense beyond comprehension, with energy densities rivaling those of the early universe. And if this matter is stable, if it has lower energy than even the most tightly bound atomic nuclei, then it may be the most stable form of matter in existence. This is the central idea behind the Bodmer-Witten hypothesis that strange quark matter is the true ground state of matter. If true, then neutron stars are not the final product of stellar evolution. They are metastable. Given enough time or sufficient pressure, they will all eventually convert into quark stars. And once formed, a quark star may be eternal, outlasting even black holes in the far, cold future of the universe. What would such a star look like from the inside? Imagine descending through the crust, a thin, solid shell of iron-like nuclei and electrons, frozen into a lattice harder than diamond. It may be only a few hundred meters thick, yet it withstands pressures exceeding 1030 pascals. Beneath it, the density rises rapidly. At first, the matter is still neutron-rich, but as you go deeper, neutrons begin to touch, then overlap, then dissolve. At a depth of just 1 or 2 kilometers, the phase transition begins. This is not a sharp boundary, not like the surface of a planet. It may be a mixed phase, where bubbles of quark matter form within a sea of neutrons, like steam forming in boiling water. Or it may be a sharp interface, where the entire core converts in a wave that sweeps outward at nearly the speed of sound in dense matter. Either way, the result is the same. A core of deconfined quarks, governed not by nuclear physics, but by the full machinery of quantum, chromodynamics QCD. And here, in the silent, crushing dark, matter enters a state never seen on Earth. The most startling possibility is that quark matter is not just a fluid, but a superconductor, not of electricity, but of color charge, the property that governs how. Quarks interact via the strong force. In ordinary superconductors, electrons form Cooper pairs, allowing them to move without resistance. In quark matter, something similar may happen, but with quarks. Because quarks carry both electric charge and color charge, they can pair up in ways that neutralize color. This leads to color superconductivity, a state predicted by theory but never observed. There are several possible phases, each more exotic than the last. Two-flavor superconducting, 2SC, up and down quarks pair up, leaving strange quarks unpaired. Color, flavor, locked, CFL, up, down, and strange quarks all pair symmetrically, locking their color and flavor states together in a highly ordered, ultra-stable configuration. Larkin, Ovchinnikov-Fulda, Ferrel, Loff, a crystalline phase where quark pairs form a spatially modulated structure, a kind of quantum crystal in the heart of a star. The CFL phase is particularly compelling. In this state, quark matter becomes incredibly stable, possibly the most stable form of matter in the universe. It breaks chiral symmetry, generates mass dynamically, and may even mimic aspects of the Higgs mechanism. Some physicists believe that if CFL matter exists, it could be absolutely stable, even at zero pressure. This would mean that once formed, a quark star could never revert to neutron matter. It would be a one-way trip into the deepest state of existence, and if a piece of it, a strangelet, were to escape, it could, in theory, convert any normal matter it touches into more strange matter. A chain reaction. A cosmic alchemist. But again, the universe has had billions of years to test this. Cosmic rays have bombarded neutron stars at energies far beyond our colliders. No such conversion has occurred. So if strange matter is stable, it likely requires high pressure to form, meaning quark stars are rare, isolated phenomena, not cosmic contagions. Still, the idea lingers, a whisper of a universe where matter has a deeper, darker form. Now, let us go deeper. At the very center of a quark star, the density may exceed 10 pi 118 kilograms per cubic meter, 100 times greater than nuclear density. Here, even the concept of individual quarks may begin to fade. In the CFL phase, quarks are paired so tightly that they lose their individual identities. The system behaves like a single quantum entity, a condensate similar to a Bose, Einstein condensate but made of fermions. It is a state of matter so coherent, so ordered, that it may exhibit macroscopic quantum phenomena, vortices, flux tubes, and collective oscillations that could be detected through gravitational waves. And because the matter is superconducting, it may carry persistent currents, flows of color charge that last for billions of years without resistance. These currents could generate magnetic fields far stronger than those in neutron stars, possibly explaining some of the most powerful magnetars. But unlike neutron stars, where magnetic fields are anchored in a solid crust, in a quark star, the field may be generated entirely, within the fluid core, a dynamo in a sea of quarks. This could lead to different field evolution, faster decay, or even spontaneous reconfiguration during phase transitions. Some models suggest that the surface of a quark star might not be a solid crust at all, but a sharp boundary between vacuum and quark matter, a bare, strange star. In such an object, there is no atomic structure, no electrons orbiting nuclei, just a wall of quark matter held together by gravity and the strong force. The surface would be smoothed down to the quantum scale, a perfect sphere with no mountains, no cracks, no features. If such a star accretes matter from a companion, the incoming protons and neutrons would be converted into quark matter on contact, releasing energy in a burst of gamma rays or X-rays. This could explain some of the most puzzling transient events in the sky. Fast, bright flashes with no clear origin. One candidate is SGR 1935+254, a magnetar that emitted a powerful fast radio burst, IF-RB, in 2020, the first FRB ever detected in our galaxy. While the burst was likely due to a starquake, some theorists have suggested that a phase transition in the core, a sudden conversion to quark matter, could have triggered it. If true, then FRBs may not just be signals from distant galaxies, they could be the death cries of neutron stars, transforming into something far stranger. But how do we test any of this? We cannot drill into a neutron star. We cannot recreate these conditions on Earth. So we rely on indirect signatures, subtle clues hidden in light, in spin, in space-time itself. One of the most promising is the mass-radius relationship. For decades, astrophysicists have tried to determine the equation of state of neutron star matter, the relationship between pressure and density. It determines everything: the maximum mass, the radius, the cooling rate, the stability. But the data has been ambiguous. Different models give different predictions. Some allow for quark cores, others do not. Now, thanks to missions like NICER, we are finally measuring these properties with precision. Take PSR J0740Pu6627, the most massive pulsar with a well-measured radius. It weighs 2.08 solar masses, yet its radius is only about 12-13 kilometers. That's small for its mass. Most purely hadronic models struggle to explain it, but models that include a quark core fit the data beautifully. Similarly, PSR JJ0300451 has a mass of 1.3 solar masses, but a radius of just 11-12 kilometers. Again, smaller than expected. And PSR J04374715, one of the closest pulsars, shows signs of rapid cooling, consistent with enhanced neutrino emission from a quark core. These are not proofs, but they are converging lines of evidence, like shadows cast by an unseen object. The more we observe, the clearer the outline becomes. Another powerful probe is cooling. Neutron stars cool by emitting neutrinos, ghostly particles that escape the core, carrying away energy. The rate of cooling depends on the particles involved and the processes that produce them. In a standard neutron star, the dominant process is the modified Urca process, which is relatively slow. But if quark matter is present, new, faster processes open up. Quark Urca, quarks decay into other quarks, emitting neutrinos, pair breaking and formation. When Cooper pairs in color, superconducting matter break and reform, they emit neutrinos. Direct Urca in quark matter, a highly efficient neutrino-producing process that can dominate cooling. These processes can increase neutrino emission by orders of magnitude, leading to rapid cooling. And that's exactly what we see in some young neutron stars. The pulsar in Cassiopeia A has cooled by about 4% in just over a decade, far faster than standard models predict. The most plausible explanation, a phase transition to quark matter around the year 2000, triggering a burst of neutrino emission that rapidly drained the star's thermal energy. It's a stunning idea that we may have witnessed in real time the birth of a quark star. Then there are pulsar glitches, sudden, spin-ups that have puzzled astronomers for decades. In neutron stars, glitches are thought to result from vortex avalanches in the superfluid interior. As the star spins down, vortices become pinned to the crust. When the stress builds too high, they unpin suddenly, transferring angular momentum and causing the star to spin faster. But in a quark star, the interior is not a neutron superfluid, it's a quark fluid, possibly in a color superconducting state. The vortices would be different. The pinning forces would be weaker. The dynamics would be faster. Some glitches are too large, too sudden, or too frequent to be explained by standard models. The Vela pulsar, for example, glitches every few years with an energy release that suggests a sudden, large-scale reconfiguration of the interior. Could a quark core be responsible? Possibly. A phase transition front moving outward could release energy and trigger a glitch. Or a sudden change in the superconducting state could alter the moment of inertia, causing the star to spin up. Even more dramatic would be a quark nova, a hypothetical event where a neutron star suddenly converts into a quark star, releasing a burst of energy equivalent to a supernova, but without ejecting the outer layers. Such an event could explain some short gamma-ray bursts or rapid X-ray transients, flashes of high-energy light with no clear progenitor. And if the conversion is asymmetric, it could give the star a powerful kick, explaining why some pulsars move at thousands of kilometers per second through space. Gravitational waves may provide the most definitive evidence. When two neutron stars merge, they deform each other through tidal forces. The amount of deformation, the tidal deformability, depends on how stiff or soft the matter is. Quark stars, being more compressible, would be more easily deformed. In the GW17-117 merger, the observed tidal deformability was relatively low, consistent with soft matter. While not proof of quark matter, it is compatible with models that include a quark core. Future mergers, especially those involving very massive neutron stars, could be even more revealing. If one of the stars collapses into a quark star during the merger, it might emit a burst of neutrinos or gamma rays at a precise moment, a smoking gun. And if the remnant survives for even a few milliseconds before collapsing into a black hole, its oscillation modes, its ringing, could reveal whether it was made of neutrons or quarks. Next-generation detectors, like the Einstein telescope and Cosmic Explorer, will be sensitive enough to detect these signals, possibly within the next decade. We are not just searching for a new type of star. We are testing the limits of QCD at high density, a regime that cannot be simulated with full accuracy on any computer. Lattice QCD, the primary tool for solving quantum field theories, works well at zero density, but fails at high baryon density due to the sign problem. So we rely on effective models, approximations like the Nambu-Jones-Lacinio model or perturbative QCD, each with its own assumptions and limitations. This is why astrophysics is so crucial. Neutron stars are nature's only laboratory for high-density QCD. They are the only places where we can observe how matter behaves when crushed beyond nuclear density. And if quark stars exist, they are the ultimate test. There is also the possibility that quark stars could interact with dark matter. Some theories suggest that dark matter, particles could accumulate in the cores of compact stars. In a neutron star, they might annihilate slowly. But in a quark star, the extreme density could enhance annihilation rates, producing detectable gamma rays. Or dark matter could trigger the phase transition itself, acting as a seed for quark matter formation. While speculative, this adds another layer to the mystery. And then there is the philosophical question, what is matter when stripped of all structure? In a quark star, there are no atoms, no molecules, no chemistry, just a continuous fluid of quarks and gluons governed by symmetry and quantum statistics. It is a state of matter so pure, so fundamental, that it may represent a return to the conditions of the early universe, just microseconds after the Big Bang, when the cosmos was filled with quark-gluon plasma. But unlike that hot, expanding plasma, quark star matter is cold, dense, and stable. A frozen relic of a phase that should not exist, yet might be eternal. If strange quark matter is absolutely stable, then quark stars could outlive black holes. In the far future, trillions of years from now, when all stars have died and galaxies have evaporated, these silent, dark objects may still exist, slowly cooling, waiting. They would be the last survivors of a dead universe. We are not there yet. We have not confirmed a single quark star, but the case is building, not from one observation, but from many. Mass radius anomalies, rapid cooling, unusual glitches, tidal deformability and mergers, theoretical stability of strange matter. Each clue is small, but together they form a pattern, a shadow of something deeper, and soon we may see it directly. The Square Kilometer Array, SKA, when complete, will monitor tens of thousands of pulsars with nanosecond precision. It could detect the tiny timing shifts caused by a phase transition in a star's core. The Athena X-ray Observatory will measure spectra with unprecedented resolution, probing the surface composition of neutron stars and possibly detecting the absence of a crust. And next, generation gravitational wave detectors will listen for the final moments on neutron-star mergers, the moment when matter may cross the threshold into the quark realm. We are on the verge. We have journeyed from the violent death of a star to the silent heart of its remnant. We have watched neutrons dissolve into quarks, matter melt into a quantum fluid, and the laws of physics stretch to their breaking point. We have traced the faint signals in cooling curves, in gravitational waves, in the spin of pulsars that suggest something deeper is happening beneath the surface of the densest objects in the universe. Now we arrive at the final threshold, not of space, not of time, but of existence itself. For if quark stars are real, if strange matter is the true ground state of the cosmos, then we are not merely discovering a new type of star. We are confronting a radical possibility that the universe has a final form of matter, a state so stable, so enduring, that it may outlive everything else. For most of human history, we believed matter was eternal in its forms. Iron was iron, gold was gold, atoms were indivisible. Then we learned that atoms could be split, that nuclei could decay, that even protons, long thought immortal, might one day disintegrate given enough time. But what if there is a form of matter so stable, so deeply bound that it never decays? A form that does not just resist change, but defines it. This is the promise and the peril of strange quark matter. If the Bodmer-Witten hypothesis is correct, then strange matter is not just more stable than nuclear matter. It is absolutely stable. It has the lowest possible energy per baryon, lower than iron, lower than neutrons, lower than anything in the periodic table. And if that is true, then every atomic nucleus in the universe, from hydrogen to uranium, is in a sense metastable, a temporary configuration, a fleeting arrangement of quarks that will, given enough time or sufficient pressure, collapse into the true ground state, a sea of up down, and strange quarks in perfect balance. In that view, neutron stars are not the end of stellar evolution. They are stepping stones. Transient objects that exist only because the universe hasn't had time to fully settle into its lowest energy state. And quark stars, if they form, are not exotic anomalies. They are the natural conclusion of matter under pressure. They are what the universe wants matter to become. Consider the timeline of a massive star. It burns for millions of years, fusing hydrogen into helium, then carbon, oxygen, silicon, all the way to iron. But iron cannot fuse without consuming energy. Fusion stops. The core collapses. In seconds, the star dies. The outer layers explode. The core becomes a neutron star. But the story doesn't end there. Over millions of years, the neutron star cools. Its magnetic field weakens. Its spin slows. And deep within its core, pressure continues to rise, not from accretion, but from the relentless pull of gravity. At some point, perhaps after 10 million years, perhaps after 1 billion, the density crosses a critical threshold. Neutrons dissolve. Quarks deconfine. A phase transition begins. It starts at the center, a tiny seed of strange matter. Then it spreads outward, converting neutron matter into quark matter in a wave that moves at nearly the speed of sound in dense matter. The star shrinks slightly, by 1 kilometer or 2. Its moment of inertia changes. It may spin up, like a figure skater pulling in their arms. Energy is released, not as light, but as neutrinos flooding into space in a silent burst. From the outside, little changes. It still looks like a neutron star. It still pulses. It still bends space-time. But inside, everything is different. The star is now a quark star, possibly a strange star, and it may remain so for eternity, because if strange matter is absolutely stable, there is no further collapse, no black hole, no decay. Just a slow, inexorable cooling, a fading ember in the dark. And if the star is massive enough, or if it accretes matter from a companion, it may grow, but never collapse. But quark matter resists gravity, not through degeneracy pressure, but through the strong force itself. It is not on the brink of failure. It is in perfect balance. This is not collapse. This is completion. And if such stars exist, they may already outnumber neutron stars in the galaxy. We estimate there are over 100 million neutron stars in the Milky Way. Most are invisible, cold, dark, spinning in silence. We detect only the ones that beam radiation toward us. But what if many of them are not neutron stars at all? What if, over billions of years, the majority have already undergone phase transitions, quietly converting into quark stars undetected? They would be the unseen. Majority. Dark, compact objects that look like neutron stars but behave differently. Their cooling curves would be steeper, their glitches sharper, their magnetic fields decaying in ways we don't yet understand. And if they are bare, strange stars with no crust, they would emit no atomic spectral lines. Their X-ray spectra would be smooth, featureless. Unlike anything we've seen, we may have already observed them and mistaken them for something else. But the implications go beyond individual stars. If strange matter is stable at zero pressure, meaning it doesn't need the weight of a star to hold it together, then strangelets could exist in space, tiny fragments of quark matter drifting between the stars. They could be as small as a nucleus or as large as an asteroid. If they collide with a planet, they could, in theory, convert it into strange matter, a chain reaction that would turn Earth into a hot, dense lump in seconds. This is the strangelet catastrophe hypothesis, a doomsday scenario that was seriously considered before the relativistic Hithy-ion collider RHIC and the Large Hadron Collider LHC were turned on. The consensus: the risk is negligible. Cosmic rays have been striking neutron stars for billions of years at energies far exceeding anything we can produce. If strangelets were stable and contagious, the galaxy would already be converted. The fact that we still see normal matter, that pulsars still have atomic crusts, suggests that either strange matter is not absolutely stable, or that the conversion process is extremely slow or requires special conditions. But the idea persists, not as a threat, but as a clue. Because if strangelets conform, even rarely, then the universe may have a mechanism for seeding quark matter. A single strangelet hitting a neutron star could trigger a phase transition, converting the entire star in seconds. And if such events have happened, they may leave behind detectable signatures, sudden dimming, rapid cooling, or bursts of neutrinos. We are not looking for explosions. We are looking for silence. Now, let us go further into the far, cold future of the universe. In trillions of years, the last stars will burn out. Galaxies will drift apart. Black holes will evaporate via Hawking radiation. The cosmos will become a vast, dark void, filled only with photons, neutrinos, and the occasional wandering compact object. In that era, neutron stars will still exist, slowly cooling, their surfaces near absolute zero. But if quark stars are more stable, they may outlast even them, because quark matter, especially in the color flavor-locked CFL phase, may be immune to decay. No weak interactions, no beta decay, no proton decay. Just a perfect symmetric state, frozen in time. These objects, quark nuggets, or strange stars, could be the longest-lived structures in existence. Not black holes, not dark matter, but cold, dark stars of pure quark matter, slowly radiating their last heat into the void. They would be the final monuments of a dead universe. And if intelligent life ever arises in that era, some unimaginable consciousness born from quantum fluctuations or Boltzmann brains, the only evidence of the past would be these silent, ancient stars. They would look at them and wonder, what were they? What force held them together? And the answer would be written in the language of quarks. But we don't need to wait for the end of time to find them. The search is already underway. The Square Kilometer Array, SKA, when complete, will be the most powerful radio telescope ever built. It will monitor tens of thousands of pulsars with unprecedented precision, detecting timing irregularities that could signal internal phase transitions. A sudden spin-up, a change in braking index, a glitch with no starquake, these could be the fingerprints of a quark core forming. The Athena X-ray Observatory, set to launch in the 2030s, will measure the spectra of neutron stars with such high resolution that it could detect the absence of a crust, a smooth, featureless emission that would suggest a bare, strange star. And next-generation gravitational wave detectors, the Einstein Telescope and Cosmic Explorer, will listen for the final moments of neutron star mergers. If one of the stars converts to quark matter during the collision, it may emit a burst of neutrinos or gamma rays at a precise moment, a signal that could be correlated with the gravitational waveform. Even neutrino observatories like Hyper Kamiokande or Dune could play a role. If a nearby neutron star undergoes a phase transition, the sudden release of neutrinos could be detected, a flash of ghost particles from the heart of a dying neutron star. We are not just building telescopes, we are building time machines, instruments capable of witnessing events that may have already happened, light years away, hidden in the data. And then there is simulation. While we cannot solve QCD at high density from first principles, we are getting closer. Supercomputers are running lattice QCD at finite density, using clever algorithms to skirt the sign problem. Machine learning is being used to interpolate between models. And effective field theories are being refined to better match astrophysical data. One day, we may be able to simulate the entire phase transition, from neutron matter to quark matter, in a virtual star. And when that simulation matches the observations, we will know. But perhaps the most profound implication of quark stars is not scientific. It is philosophical. For centuries, we have believed that matter has a hierarchy: atoms, then nuclei, then protons and neutrons, then quarks, each layer more fundamental than the last. But in a quark star, that hierarchy collapses. There are no atoms, no nuclei, no particles in the classical sense. Just a continuous field of quarks and gluons, a quantum fluid where individuality dissolves into collective behavior. It is a state of matter so pure, so symmetric, that it may represent a return to the conditions of the early universe, microseconds after the Big Bang, when the cosmos was filled with quark-gluon plasma. But unlike that hot, expanding plasma, quark star matter is cold, dense, and stable, a frozen echo of the beginning, preserved in the hearts of dead stars. And if such matter is eternal, then the universe may have a preferred state, not of expansion, not of entropy, but of stability, a final form, a resting place. We do not know yet whether quark stars exist. We have no direct proof. No smoking gun. No telescope has yet pointed at a star and said, "This is made of quarks." But the case is growing. Every anomaly in mass and radius, every unexplained cooling curve, every glitch that defies models, every merger that deforms too easily, they are not proof, but they are invitations. Invitations to look deeper, to question our assumptions, to consider that the universe may be stranger than we imagined, because in the end, the cosmos does not care about our categories. It does not care whether we call it a neutron star or a quark star. It only obeys the laws of physics, laws we are still learning to read, and in the hearts of dead stars, those laws may be writing a new chapter. One written not in neutrons, but in quarks. One written in the language of the impossible. One that begins not with light, but with silence, and ends not with collapse, but with revelation. The next neutron star we observe could be the first quark star we've ever seen. We just don't know it yet. But we are listening, we are watching, we are calculating. Because in the search for the densest matter in the universe, we are not just studying stars, we are learning what matter and reality itself can become. And when the signal finally comes, a radius too small, a temperature too low, a spin too sudden, we will be ready. Because the universe always reveals its secrets to those who dare to look.